Hello everyone, welcome to the Control Theory seminar series. Today we are very excited to have Sushrut Karmalkar as our guest speaker. Sushrut is a postdoctoral researcher with Professor Ilyas Diakonikolas at the University of Wisconsin at Madison. His research interests lie in the area of machine learning, computational learning theory, and statistics. His work focuses on developing principal algorithms which are efficient and robust to input misspecification. Today he has very kindly agreed to give a talk on tackling label corruptions. Let's welcome Sushrut.
Thank you. So today I'll be talking about tackling label corruptions, and we'll discuss this through the lens of two problems. The first is univariate polynomial regression, and the second is generalized linear models. So to set the stage, consider the problem of linear regression. So just univariate linear regression, where you're given samples xi, yi, where y equals w star dot x plus possibly some noise, right? And the goal is to recover w hat such that w hat minus w star is small. So you have data that looks something like this. And the typical solution here is to use the L2 minimizer, which is this linear regression. So unfortunately, even a single label corruption makes this solution deviate significantly. So I could make that red dot go as high as I want and arbitrarily corrupt the line that I would recover. So this leads us to a natural question, which is, can we design efficient algorithms that can tolerate arbitrary label corruptions? Right? So you want to recover the same solution or roughly the same solution, even after the label has been corrupted completely in an unconstrained manner. So there will be three parameters of interest for us. The first is the fraction of corruptions we can tolerate. The second is the sample complexity, and third is runtime. Now, the first two have been studied in detail back in the 60s by Tukey and Huber for various problems. But the goal there was to find statistically optimal estimators. So estimators that got good sample complexity for that particular fraction of corruptions. But these estimators sometimes were not computationally efficient. So starting from work by Diakonikolas, Kane, Kamertz-Lee, Moitra Stewart, and Lyra Wempel in 2016, there has been a greater focus on getting algorithmic, that is efficient algorithms that can do the same job. So these algorithms were for robust mean estimation, but what we are going to study today is, so robust mean estimation is an unsupervised learning problem. Here we are given a supervised learning problem. So you're given x, y, and you want to find the relationship between them. So it's slightly different, but along the same lines. So here's the broad outline of the talk. We'll first discuss robust polynomial regression, then we'll talk about robust GLM regression with oblivious noise, and then we'll finally summarize these results. So this is joint work with Daniel Kane and Eric Price, and this is from Fox 2017. So we'll first have a short introduction. I'll state the main theorem and then discuss the ideas, and finally we'll state the algorithm. So the version of polynomial regression that we'll be studying today is as follows. You're given samples xi, yi, where xi lie between -1 and 1, and y's can be any real number, such that pointwise yi's are close to p of xi. Okay, where p is a degree d polynomial, and you may assume that the xi's are drawn uniformly from -1, 1. So it's a simple problem, right? And the goal is to recover p hat such that p hat is close to p pointwise in the interval -1 to 1. So you get to see these blue points, and perhaps the original thing is this blue curve here. And from these blue points, you would like to recover another degree d polynomial, which closely approximates the original at every point, right? So this is not on average. This is not, squared loss or anything. At every point, you want a good approximator. Now, yes.
Their degree degree is fixed there, or
Okay, the degree of p is fixed and known, and what you want to recover is p hat, which we want to have the same degree. Yeah. Mhm. Right. So I think the way to think about it right now is p hat and p will have comparable coefficient sizes up to a log factor. This will actually come up in the algorithm. Interesting. Okay. No, sigma is just some real number. You know, pointwise, they are this close. That is all that is told.
Point if you want average or something, then
That is actually easier. Yeah. Okay, our model is, the adversary can take a point and then corrupt its y coordinate as much as it wants. So there are two possible variants. The first is there are randomly chosen x's for which the adversary may corrupt y as much as they want. And the second is the adversary gets to choose the x as well as the y. Right? Let's see what happens here. Unfortunately, if the adversary gets to choose both x and y, the problem becomes not identifiable. So even for a fraction of corruptions going like 1 over the degree of the polynomial, you can have two polynomials which are valid given the observations. So if you look at this picture here, the dashed red line, these are your observations. They sort of flatten out here. These are your corruptions. Okay. And the dotted orange line is the zero polynomial, and the blue line is a scaled Chebyshev polynomial. What it is not so important. The point is that width is 1 over d. And so if given the red dashed thing, it's indistinguishable whether your polynomial was 0 or whether it was this blue curve. So it could be either one of these two. Yeah.
you can arbitrarily change the degree of the polynomial.
Yes.
Then block it.
The corrupted points may not even, yeah. The corrupted points have no this thing.
So then, like, what are we even trying to recover? You said the polynomial that is.
There is an original polynomial. It gets corrupted. You want to compete with the original polynomial.
You said that the degree has to be had and be.
Right. So you want to compete with the original polynomial with another polynomial having the same degree. So there is a degree d original polynomial. It gets corrupted, whatever. And you want to find p hat, which matches the degree of the original polynomial and gets good guarantees.
We have multiple polynomials which have same degree and within this.
Yes, then you just return any one of them. Yeah. Right. The issue here is the L infinity norm is bigger than d over 2. So you have two polynomials which are actually very far apart, which the same data can explain. So if you allow the adversary to corrupt both the x's and the y's, this is what happens. So okay, we are going to stick to the first one. And this was actually a formulation due to Aurora and Court in 2003. So here you're given samples x comma y such that x's are uniformly drawn from -1 to 1. And with probability 1 minus epsilon, you get, as I described before, yi being close to p of xi, right? And with probability epsilon, yi can be arbitrary. So the adversary can set yi to be anything at all. And in this model, you want to recover p hat such that the supremum over -1, 1, p hat minus p is at most order sigma. Okay, so yeah, so the important thing is with probability 1 minus epsilon, you're good. With probability epsilon, you're bad. And the question is, how large can you get epsilon to be so that you can still efficiently record a good answer? Yeah, so your data looks something like this, and from this you want to recover your solution, right? Not so obvious. So back in 2003, Aurora and Court showed a linear program when there are no corruptions for how to solve this problem. And if you just run ransack, it turns out that tolerates an epsilon, which is like log d over d, fraction of your samples being corrupted. In 2016, Guruswamy and Zuckerman showed an algorithm which tolerates all the way up to 1 over log d, fraction of your samples being corrupted. Okay, so there's been slow improvement until this Guruswamy-Zuckerman result. And their algorithm was they sort of modified a cryptographic based algorithm to do some sort of, robust regression here. So this was their result. They showed that there exists a polynomial time algorithm which, given d square or epsilon square samples from the uniform distribution or -1 and 1, an epsilon fraction of which are outliers, where epsilon is less than 1 over log d, with high probability recurs b hat satisfying this closeness condition, where it's sigma times some quantity which depends on the L infinity norm of p, but polynomially so. Right, so it goes 0.001 polynomial L infinity norm. So they also get an improved rate, O tilde d log d samples, if you sample from the Chebyshev distribution instead of the uniform distribution. The Chebyshev distribution is just a distribution whose PDF goes like that, 1 over root 1 minus x squared. Okay? And in our paper, what we do is we first replace that epsilon by 0.5. So we go all the way up to the information theoretic limit. So it was 1 over log d, we can get it to 0.5. And we replace this dependence on, L infinity norm of p by 2.01. So it's a constant. And we also remove these extra log terms. Okay, so we have an algorithm which basically cleans this up and gets you the correct guarantees. So this is what we say. We say that, oh, there is a polynomial time algorithm which, given d square samples from the uniform distribution and all the way up to half your samples being corrupted, recurs with high probability p hat, which is order sigma close to p in L infinity norm. And okay, so the same thing for the Chebyshev distribution. We can do it in d log d samples. So the ideas are actually quite simple. There are two main ideas. The first is degree d polynomials don't change a whole lot in a small interval. So if you had a tiny interval here, the degree d polynomial is not going to change like this. It's going to change something like this. Okay, and more precisely, there is an inequality which says that the derivative of a polynomial in this -1 to 1 range is at most d squared times its maximum value. The second idea is that basically, if more than half my points are inliers, then if I look at the median of these points, these will also be inliers. This will also be an inlier. So if less than half my points are outliers, the median will always be inlier or close to the true median. Okay? Yes, yes. So you have to have a bounded range. I mean, if you have an unbounded, you can, depending on the range, you'll have other parameters coming up here. So, yeah. Right? So this actually suggests a very simple algorithm. First, you partition the x's in a fine interval of some sort. Then, for each interval, to determine your yi, what you do is you just take the median of those guys inside. Since with probability at least half you have a good sample, it's going to most likely be a good sample, and then xj you can just pick arbitrarily. Okay, so this gives you a new data set, y tilde j and x tilde j, right? A new set of points which is cleaned up in some sense. Yeah, yes. So tau is the, okay, so you have these many uniform, so tau, so you choose tau depending on how many partitions you need. Yeah. Cleaning up is happening by taking the median for the y's. So the y's are very noisy, right? That is the issue. But the y's are chosen, how does the adversary curve the y? At random, it gets an opportunity to replace the y with anything it wants, right? But that probability of corruption is less than half, right? So at least half the points in this bucket, if you sample enough, at least half the points will be good. Yes, yes, yes. At least half the points will be good, and if you take the median, that will then be a good median. Approximately a good median. And that is what actually happens. So you get this cleaned up data set, you fit a degree D polynomial, and you return R. So now there's a small problem, which is what you have is an approximately good point for y, right? So you get an additional error of tau times the L infinity norm of P, which is not too dissimilar to what the previous result had. So now we need to get rid of this quantity to finally get the right rate. Yeah, so we want this to be order sigma. So to get order sigma, turns out you can do, oh yeah. Aurora and Cook, yeah. Yes, yes. Kind of. I mean, well, essentially you can write this L infinity minimization as an LP program, and that's what essentially they do. Yeah. So yeah, so there's just this small issue here which you want to fix. And the way you do it is we are going to use this previous algorithm and we're just going to bootstrap it on itself. So you start with a good approximation. So you just run L1 regression. It turns out L1 regression is going to give you a bad guarantee, but it's controlled. So you're going to get L infinity error p square times sigma. Okay. Then what you do is you look at p minus p hat 1. This is a degree D polynomial. P hat 1 is the polynomial you found by L1 regression. P is the original polynomial. Difference of two degree D polynomials. So this is a degree D polynomial. And you look at the samples given by y minus p hat 1 of x, that particular x. So you can get a sort of, your goal changes. Your goal is to attempt to record the residual. Now let R be the record estimate of p minus p hat 1. And you update P2 with R plus P hat 1. So you got P hat 1. Then you looked at the error between P hat 1 and P, and you try to estimate that. The error itself is a polynomial, so you can do this. Okay. So what you then see is you have P hat 2 minus P, which is this. But you knew that, P hat 1 minus P had this guarantee. And using the previous the estimate from the previous slide, you have 2 sigma plus tau times the L infinity norm of this difference. Okay. So this is just one step, but if you keep doing it, you can essentially get this guarantee by sort of telescoping some. And you choose tau to be less than 1. So in logarithmically many iterations, you kill this. And this can be, it's still going to be a small constant. So you can get this to be order sigma. Right? So there's first a simple cleaning up of the data and then estimating some polynomial. But unfortunately, that doesn't give us quite the guarantee that we want. But it turns out that it gives us a pretty good guarantee, which we can then put on itself to sort of improve the rate. By subtracting your current estimate from the data and then continuing to get better and better estimates. So the algorithm is as follows. So you start with your initial estimate p hat, which is just the L1 regression. Then you uniformly partition your interval minus 1, 1, and you repeat the following log 1 over epsilon d times, which is you look at the median of your cleaned up data, choose an arbitrary xj for each interval, fit a degree D polynomial minimizing these guys, and then you update p hat by your next to get your next estimate. Right, so there's a slightly different algorithm to get the optimal d-log D sample complexity, but it's essentially the same. The what you sample from is going to differ, and so some of your updates will change, but other than that, this is the idea.
When you divide this space into this histogram kind of thing,
Correct.
instead of like this, you will take any arbitrary angle.
But there's no okay.
I mean, you can take maybe some theta angle and create this fix.
Sure.
And then take the median of those, probably that will give you a correct sample as well. So,
But
okay.
okay.
Is it special to have this, or you can have any angle and do the same and it will be same?
Okay. So in principle, I guess you could have any angle, but I don't quite know how to fit it together because this Markov brothers inequality tells you about the derivative. So I know that in a small interval, this thing is going to change by not too much. But if I do this, then it could change by a whole lot. So yeah, I prefer to use this because I have control over the derivative.
Then did we use that control over the derivative?
So good question. When you get when we cleaned up these samples, right, you incur an error. In fact, that error is this guy. So if you didn't have control over the derivative, then when you took the median, it could have been very far away, and that will be reflected over here. In fact, this is how far you could be from the, so if you recall these, so it's in terms of max of P. So this is the L infinity norm of P. So it's D square max of P, and the D square can be taken care of by choosing a fine enough partition, but you still suffer a small extra error in terms of the L infinity norm of P, which you don't know, so you can't control explicitly. Yeah, okay, so good. There are some extensions one can think of. Let's wait. Are there any other questions? Yeah. Yeah. Correct.
Like in situations where, let's say, the corruption is also nice in some sense, it's some kind of corruption.
I see. So in situations where the actually, okay, this is strictly speaking, like you need D samples to recover anything at all for a degree D polynomial. So D log D is good regardless. So yeah, we can do D log D with the Chebyshev distribution, and I don't think you can do better, at least naively. So okay, maybe if it's Gaussian mean zero noise, then you can just average a bunch of these guys and perhaps like that make an improvement. But yeah, you'll just be shaving off log factors. Okay. So there are some natural extensions. First is, okay, what about high dimensional polynomial regression? Okay, that turns out to be too hard, but what about high dimensional linear regression? Turns out even for linear regression, getting a guarantee like this is not possible, right? You wanted something pointwise close. That you cannot do. But you can do squared loss. You can get something which can tolerate, a large fraction of your samples being corrupted in the same noise model. And L1 regression just works. It'll just clean it up. It'll do a good job without like no modification. So there is another model which is completely adversarial corruptions, where both X and Y are corrupted for the linear regression case. Okay. Here, it turns out that if you allow the algorithm to output a small size list, then you can even solve this problem when epsilon, which is the fraction of corruptions, is very close to 1. So with 99% of your data being noisy, you can output a small size list, something like, okay, if 99% is corrupted, then you'll have a list of 100 candidates, such that one of them is in fact very close to the true answer. List of linear functions. So this is the list decoding setting. We'll come back to this in the next part of the talk. But yeah, so for high dimensional linear regression, you can have a very noisy setting where 99% are very corrupted, and this was joint work with Adam Clivens and Pravesh Kothari, and concurrently Raghavendra and Yao also had a similar result, but with different clue. So this actually has found applications in robotics. So it turns out someone actually wrote up this code, which is a sum of squares program, but it turns out for 3D images this can be done, and it's very useful for image stitching, where maybe you have some fraction of your pixels being dead pixels, so you can't really get the correct measurements. But so you have two images, one of the same thing at angles to each other, and you want to stitch them together in a way so that it feels like a continuous correct image. And so this is just a linear problem, right? So you have A comma B. A is the point in this image, B is the point in that image, and they're related to each other by a rotation. And you just want to recover this rotation. So it is a linear regression problem of some kind. The only issue being some of your data is bad because some of your correspondence are not going to be correct. And it turns out you can actually run this code and it can recover multiple rotations sometimes depending on how many fraction of your pixels are there. Okay, so with this, we'll move on to robust GLM regression with oblivious noise, unless there are other questions. Okay. So this is joint work with Ilias Diakonikolas, Jong-Ho Park, and Christos Samos. This was at this Colt, which was just a week ago. So the problem of GLM regression is the following. Okay, given n samples of the kind x comma y, such that y is g of w dot x, where g is a one Lipschitz monotonically increasing function. Okay, return w hat such that the L1 loss between g w star dot x and g w hat dot x is as small as can be. Right, you choose delta. So you get to see points like this, and you need to recover w star such that g of w star dot x over here, your w hat matches g of w star dot x as well as it possibly could. So we'll refer to this quantity as the excess loss, the L1 distance between w star and w hat over here. G is some arbitrary one Lipschitz monotonically increasing function. It is not. It is not. Yes. So this is, for instance, a ReLU, but it could be anything else.
This is like the Markov.
Lipschitzness does control the derivative. Yes, yes. So yeah. So the first thing is, in general, the excess loss is non-convex, but it turns out that if the x's are drawn from a good distribution, you can get arbitrarily accurate recovery for g being the ReLU function via gradient descent. So this was shown by Soltano Kotabi in 2017. But naturally, the question we are trying to ask is what happens when there is noise? So you have something like this. And there are two typically considered noise models for this problem, for these kind of problems. So first is adversarial label corruptions, where the adversary gets to inspect your data and chooses to corrupt a small fraction of your samples arbitrarily. And the second is agnostic learning, where the goal is to recover a hypothesis with loss competitive with the best fitting function to the data. Right? So the loss of what you find should be comparable to the loss of the best fitting function to your data. The data has no constraints a priori. In both of these settings, unfortunately, you have hardness results. So these are computationally hard. You cannot, in fact, solve the problem for these settings in polynomial time. Even for approximate recovery, as well as if you make assumptions on the distributions. Right? So this, so in this paper, what we try to answer is how aggressive can noise models be for GLM regression while still allowing for efficient algorithms, right? So the noiseless setting was solved, good, and the noisy setting, two typically considered noise models are too strong, right? So what is the strongest you can get? So this is the noise source we consider in our paper. So an alpha sigma noise source generates x comma y such that y equals g of w star dot x plus some oblivious noise plus additive Gaussian noise. Now the oblivious noise, that's the C that I've written there, is independent of x, and the additive Gaussian noise is also independent of x. But the only constraint on the oblivious noise is that the probability that it takes the value 0 is at least alpha, and alpha can be little of 1. Okay? So what that means is alpha could be like 1 over dimension. So as the dimension increases, this is a vanishingly small fraction of points where the C is 0. So we are in, once again, the dense noise setting. Most of your samples are going to be corrupted by noise, and there is no control over this noise, but the noise is independent. Right? Great.
Do you need the Gaussian noise?
Oh, we don't need it, but it is actually easier to do it without the Gaussian noise. But with the Gaussian noise, it turns out you need to do something more. So, okay, without the Gaussian noise, here is what I would do. Without the Gaussian noise, I would, if it were a ReLU, other things might be different, but if it were a ReLU, I look at all those y's which are 0, and that will give me that will tell me that, oh, you know, behind this line, all my samples are 0, so my any vector that separates these points from the others is good for me. But Gaussian noise sort of makes things more complicated. Right. So yeah, so what I'm saying is this is something like the ReLU function. Anything to this side is 0, right? So if I identify W star correctly and I project in this direction, then it should look like that, right? So what I'll do is I'll look at my high dimensional data, look at all the y's that are 0, and simply find W star which separates those points from the others, and that will be a reasonable candidate. So Gaussian noise just makes things harder, but you don't need Gaussian noise. Yeah. Okay. So this also generalizes heavy-tailed noise, which is something that's considered often. Heavy-tailed noise is noise which is independent noise, but the tails might not go as e to the minus x square, which are the tails of a Gaussian. It will be less concentrated. But since we make no assumptions on what this guy is, basically any tail behavior is acceptable as long as you can split your noise into these two pieces, which is one piece which has some mass at 0 and the other piece which is Gaussian. Gaussian is not so important. All that matters is you have some density near 0.
Sub-Gaussian or?
That's also fine. Yeah. Okay, I think we can do better than just sub-Gaussian, but sub-Gaussian is also fine. Right, so this has been well studied in the context of linear regression. There have been lots of works, and people have come up with algorithms that can tolerate up to 1 over d to the c, where c is some small constant. So a polynomial number of fraction, a polynomially small fraction of inliers. But all these papers make assumptions on the oblivious noise or marginals. For example, they assume that the x's have some sort of sub-Gaussian distribution, or they assume that the oblivious noise is independent and unconstrained, but also symmetric. Something like this. In contrast, the result I'm going to show you now, we make no further assumptions on the noise. So what you saw there is what it is. No assumption on x beyond being polynomially bounded in norm. So the norm of x is polynomially bounded, but other than that, no more assumptions. And our algorithm applies to generalized linear models beyond just linear functions, which is the case for linear regression. Okay? And also we can get arbitrarily accurate recovery. Okay, so this is our setting. given m samples, xi comma yi, from an alpha sigma noise source, which I just described, the goal is to return a polynomial sized list of candidates, one of which has excess loss delta. Okay, and the assumptions are xi and the norms of xi and w star are polynomially bounded, and g is monotonically increasing in one Lipschitz. Okay, so now you might notice, okay, I said we'll output a small size list of candidates, not a single candidate. Unfortunately, if you make no assumptions on x, this is the best you can do. So your data could, for instance, look like this. And now there are two solutions which are identifiable from the data but are far apart. So it could be that the green thing above is the true solution and the oblivious noise sort of shifts you down with probability half. Or it could be that the true solution is the thing below and the oblivious noise sort of shifts you up with probability half. And you can't distinguish between these two just given this data. So since there is no uniquely identifiable solution from the data, in this context, we do need to output a list of candidates to cover all these potential guys. We have two theorems. The first is this List-decoding theorem. Here is this notation. Delta is the desired accuracy. R is an upper bound on W star and X. Sigma is the variance of your Gaussian noise, and alpha is the probability of being an inlier. So there is an algorithm which takes as input delta, alpha, sigma, and R, draws m samples from an alpha sigma noise source, and returns a polynomial sized list containing w hat, which achieves an excess loss of at most delta. Okay, so everything is polynomial, and great, we find w hat, which achieves low loss. Now, it turns out that if the data is identifiable, then we can actually do better. So we have a condition for unique identifiability. Why this comes up, perhaps will come up, we can explain later. So you say W star is uniquely identifiable if for any U achieving excess loss at least delta, GU dot X minus GW star dot X is anti-concentrated. Okay. This will come up again, and so we will discuss this in more detail. But for now, we have this precise condition which allows us to get unique identifiability. And so if that holds, we have a second theorem which says if W star is uniquely identifiable, then there is an algorithm which takes delta, alpha, sigma, R, and tau. Tau is this parameter which captures the amount of anti-concentration in bit of that quantity, right? This difference that I showed you, right? There's an algorithm which takes all these parameters and a list containing W hat, which is very close to W star, and then draws another polynomially many samples and returns a single candidate, achieving an excess loss of delta. So we have two theorems. The first one says we can always find a list. The second one says if you are identifiable uniquely, then by paying a little more, you can in fact prune the list down to a single candidate. Yeah. Yeah. So it is qualitatively necessary. The exact parameters might be a little off in the Okay, good. So here are the ideas for the theorems. So for now, assume the noise has median 0, but we can handle any median. The idea is to design a gradient oracle which basically satisfies the following, which is the inner product of the gradient with the direction that you want to move in. So we're going to use online gradient descent. But so as usual, you want to show that it is correlated with the correct direction that you want to move in. And as long as you can show this, then online gradient descent will obtain a polynomial list of potential candidates, one of which is close to the correct answer. Okay, so this is just known guarantees from online gradient descent. So the goal here Our focus is to design the correct gradient oracle. And the natural gradient step is to just take the gradient of the loss, right? So if we had this excess loss, which was expectation of g of w star dot x minus g of w hat dot x. We don't have access to g of w star, but you can replace that with y, right? So you can just ask what is the gradient of the L1 loss. It turns out to be this, right? Unfortunately, this doesn't work, and I'll show you why. And if you just knock this guy out, g prime dot w dot x, then this gradient oracle seems to work out. Not seems to, it does work out. So here is an example that shows you what can go wrong. Let x be drawn from the two-dimensional unit ball, and noise is this, standard deviation 0.25. Let the oblivious noise take value minus 3 by 20 with probability 0.3, 3 by 20 with probability 0.1, and 0 otherwise. Right. Here's what happens. This is what your natural gradient would look like. And here's what happens once you correct for it by just dropping the g prime term. And why this happens here is, okay, in this context, we said g to be the ReLU function. But why this happens is that the third term goes to 0, near 0. And basically turns out knocking that out actually just fixes it, shaves off this thing. Yeah. Okay. So that is it. So that is the main idea for this list decoding part, which is you just design the correct gradient oracle. It's pretty simple. You run online gradient descent. There are some tricks to deal with this median zero business that I assume, but it's not very hard. So, okay, pruning is more interesting. So recall our definition of unique identifiability. So W star is uniquely identifiable if for all u with excess loss at least delta, g u dot x minus g w star dot x is anti-concentrated. Okay, so here is how you should think of it. So look at g w hat dot x minus g w star dot x. Okay, for some w hat. Suppose w hat were equal to w star, right? Then this difference would be a flat line, right? But it is not. Since it is not, there are some points where it might be greater than 0 and maybe less than 0. And what you can do is you can partition the data x's into two sets. One where things are around 0 or less than 0, and the other set where things are bigger than 0. If you can accomplish this, then you know g of w hat and g of w star are different, right? If they were the same, you could never do this because the noise is independent, and so the value 0 will occur at the same quantile in both partitions, as long as the partitions are somewhat big. So this is the idea. So you reject w in your list if the quantile at which gw.xi minus yi is 0. So there is a quantile at which this quantity is 0. Differs between any partition set of samples. So across all possible partitions, if there is some partition such that this being 0 on one side, so 0 occurs at say the 50th quantile, whereas on the other side 0 occurs at like the 30th quantile or something, then you know W is to be rejected. Okay, else except W. So why is that? Well, if you look at this quantity, this is the same as this plus the noise. The noise is independent. As I said, if W hat were equal to W star, then this would be 0, and no matter what partition you take, 0 will occur at the same quantile since you're just drawing IID samples from the noise distribution, right? On the other hand, if these are not equal, then or these are not close by, then you will find some deviation. So yeah, if this difference is not anti-concentrated, then the excess loss has to be at most order sigma. This is the counterpositive of this. So, okay, but how do you choose the partitions? Okay, so I said across all partitions, but there are potentially, a very large number of partitions. So what you do is you have your list. You know that in your list you have a good candidate, right? So what you do is you look at candidates between your list and you sort of put them against each other to determine the set of partitions. So you choose Wi and Wj in your list. You can then compute this guy, and you can then compute for the x's. The x's are not corrupted. For those x's, you can compute which points get high loss, high difference, and which points get low difference. And then you use this partition and you test what happens with Gwi minus y, for example. Right? Now, since one of the candidates is very close to W star, at some point you're going to find the correct partitions for that particular y. Okay, that is the main idea. So to summarize, we discussed two problems: univariate polynomial regression, where we designed an efficient algorithm which is able to tolerate up to the information theoretically optimal rate of corruptions possible, and also GLM regression with oblivious noise, in which we design an algorithm which records a polynomial sized list of candidates, one of which achieves low excess loss, and if the setting is uniquely identifiable, returns a single candidate. Yeah. Thank you.
Do we have any questions for the speaker? So in the second problem, so you are assuming that the function is one Lipschitz.
One Lipschitz, yes.
Can you tell it to like Lipschitzness?
Yeah, if it's L Lipschitz, then there'll be a polynomial dependence on L. Polynomial dependence on L. Yes.
So I said, even if we talked about this noise, you can have it first version, but like for other sort of epsilon noises, which are like, what do you expect?
Oh, so okay. What will happen is this. Okay, so this guy occurs here, right? Omega alpha, alpha. In this omega, hiding is some dependence on this added noise distribution. So if your added noise distribution is super anti-concentrated, then there will be some constant here which will become really, really tiny. So your gradient oracle will basically not be the most ideal, but it will still work out. We'll just take more steps. You need to estimate things to a finer accuracy, stuff like this. So yeah. So depending on depending on this guy's density near 0, that thing changes a little bit. Yeah.
Okay, so do you have any questions? Let's thank the speaker again. Small token of appreciation from our side.
Thank you.